Now, what is a path-connected topological space? So a path-connected topological space means that if you take any of its 2 points, then there is a path from x to y. So, and such path is represented by a continuous function from the interval to x, such that s of 0 is x and s of y is 1. So, I don't know, speaking of subsets of, say, of the plane, right? So if you take anything kind of, so something like this in the plane, so the shaded region is not there, right? So this is path connected, right? So you take any point, any 2 points, and there is a path from the first point to the second point, right? But uh, if you have something else here, something else here, and everything in between, oh sorry, everything between them, so I'm going to shade the outside exterior of this, right? So the region that is not shaded now is not path connected, because it is possible to find 2 points such that they cannot be joined by a continuous path within my x. So if my x is these kind of 3 unshaded parts, then there is no path from this point to this point. So this is not allowed because it goes through something that is not in our topological space. So let me show you that path-connected subsets of the real line are all intervals. So I'm going to prove it. So suppose that we have x is a subset of the real line, and x is path-connected, right? So suppose that a 2 points a and b belong to x, right? So it means that there exists a function s from 0, 1 to x, such that s of 0 is a and s of 1 is b. Well, now consider any point between a and b, right? So let's say u is between a and b. But then, since our function s is continuous, according to the intermediate value theorem, so s of 0 is a, s of 1 is b, and u is between a and b. So it means that there exists some point, some t, such that s of t is u, right? But everything that is in the image of s is also in x, so u must be in x. So in other words, it means that if 2 points a and b belong to x, then the whole interval from a to b is a subset of x. Well, then it means that x itself is an interval. I mean, it may be open or closed, may be infinite or finite, but it is an interval. Because together with every 2 points in x, the whole interval, the whole closed interval from a to b is still an x. All right, now, path connectedness is similar to compactness in that a continuous image of a path connected space is again path connected. So let me prove this. Again, it's just like for compactness, it's kind of is not very hard to prove. So let me do it. So suppose that we have 2 points, a and b, belong to f of x, right? So it means that a is f of x and b is f of y for some x and y in x. And so let me draw it. So suppose that this is my x, so f goes to y, and this is the image kind of f of x, and there is a point a here, a point b here, right? And these 2 points a and b, they come from some points x and y, so this x is mapped to a and this y is mapped to b, right? But there exists a path from x to y, right? So there is some path from x to y. So this path is a function from 0, 1 to x. But then we can just take the composition, right? So the composition of that s and f, right? And then you see that f composed with s, if you apply s first and then f, this is going to be a function from 0 to 1 to y, and this is going to be a path connecting a and b, obviously, right? Because by construction, um, f of s of 0 is a, and f of s of 1 is b, right? So f composed with s is therefore a function from 0, 1 to y, that connects a and b, right? So this is how we construct a path from a to b. So a continuous image of a path connected space is again path connected. So here is how we can apply it. So any surface represented as a plane model is path connected. I mean, we can either see it directly, like if you have, say, a torus. It doesn't matter which plane model, say a torus. So if you take any 2 points, to like one point, another point, you can join them by a path. But from another perspective, um, such a torus can be thought of as a continuous map um, from the square. So this is just a square as a projection to the quotient space. Yeah. So because our torus is the quotient space, and a square is of course path connected, but then its continuous image, so the projection under the projection is again going to be a path connected. So and every surface, well, every well, yeah, so every surface represented as a single polygon, so plane model by a single polygon, is the continuous image of that polygon, so therefore it is path connected. All right, and finally, there is a nice theorem that combines compactness and path connectedness. So if we have any compact path connected topological space, and if we have a real valued continuous function on that space, then this f is bounded, attains its maximal and minimal value, and also has the intermediate value property. So why is this true? Is because f of x is a subset of the real line. It is path connected. Since it is path connected, it means it is an interval. On the other hand, f of x is compact, since x was assumed to be compact. And since it is compact, it means it is not an any interval, but it is a closed interval. But if f of x is a closed interval, it means that f of x is just, well, we're going to denote its left endpoint by m and its right endpoint by m. But essentially, so notice that the statement of the theory is essentially equivalent to saying that the image of our function is some closed interval. So that's it.